Welcome everyone and good evening and welcome to tonight's lecture of the North of England Institute of Mining and Mechanical Engineers. And well, we've got a very good talk tonight, so I'm not going to mess around. So without delaying too much, we'll conduct our short procedural agenda with apologies for members' absence. Does anyone have any members' absence to declare? I can declare Derek Newton.
Yes, Derek Newton, Rick Smith, and Stevie Davidson. Unfortunately for tonight, that's all I've got, Steve.
Yes, well, that's probably all I've got too. So
lovely.
Wonderful. Let's move on then. Andrew, the Honourable Secretary, will now read a brief explanation of the minutes of our last lecture for approval by Council.
Yes, so we had an excellent meeting last in March, so 2 months ago. Our last month's meeting was actually the two-day Energy Institute conference, joint conference with the Durham Energy Institute, which we'll get to in a moment. But our March meeting was Martin Dade Robinson, again from Newcastle, on living construction. It's a really interesting talk on how all sorts of living and organic materials could possibly be useful in construction, and a rather nice attendance and a good few views on YouTube as well, with some questions predominantly about how useful these materials are in a home setting for furniture. So if that's all right, Steve, as a record of the meeting.
It is indeed. Wonderful.
Lovely.
That's approved.
Our next meeting is our last of the 2020-21 series, and it's structural degradation landscaping, joint lecture with the Henry Royce Institute, and it'll be given by Dr. Bill Hedges, corrosion consultant and also president of the Institute of Corrosion. So this is looking at how we can possibly prevent corrosion in all of our predominantly steel assets, but also for hydrogen, CCS, and all sorts of other things as well. So it should prove to be a very fascinating talk indeed. So I'm grateful to the Royce Institute for partnering up with us on this one. Our other notices are the JF Tunnicliffe Medal, which we're looking for entries to. This is open to any engineer under the age of 35 across all sorts of raw disciplines of engineering, so do please get in touch. The closing date for this is Friday the 16th of July. More details at mininginstitute.org.uk. Just look up the tab on prizes, awards and medals, and you'll find more information there, and also information on how to get in touch and enter. But we're looking for entrants, and we'd be very pleased to hear from you. Don't forget, of course, you can follow us online for all of our events on Twitter, Facebook. You're currently probably watching on YouTube, and any members from the engineering group of the Geological Society of London are warmly welcomed as well. I hear some of you are along this evening. We have a large range of events and activities which we usually hold in person in Newcastle and in Durham, from lectures and conferences that you're at today. We'll hopefully having our annual dinner again this autumn, where a range of professional men and women from across a range of engineering disciplines get together and discuss ideas and have a very nice dinner as well. We're looking into more CPD and also socials again, social events once we can come back. And also we've previously had local field trips, but we're also looking forward to eventually getting to these Polish mines I keep talking about for the last year. As I said, it's do please like, share and subscribe via YouTube. Our last April event was actually the Northern Energy Transition Conference, again jointly with the Durham Energy Institute at Durham University. All the videos from that are currently being edited and should be available on YouTube within the next few weeks. So do please check back, hear about some excellent speakers from geology, materials science, and a range of other topics as well. Don't forget, if you're watching this evening via the internet and you're not already a member, we have a range of excellent membership benefits, so please go to mininginstitute.org.uk/membership and find out more, and we look forward to receiving your application. So there we are, Steve, that's the notices for today, and I'll hand you back.
Thank you very much indeed, Andrew. Well, we have great pleasure in introducing tonight's lecture by Professor Stephanie Glendinning. Stephanie has a Bachelor of Science in Civil Engineering gained in 1989 and a PhD in Geotechnical Engineering gained in Loughborough in 1995. and has great experience as a civil engineering academic specialising in infrastructure and adaptation measures required to sustain protection from extreme weather events and climate change, with particular expertise in ground modification. I hope I'm right there, Stephanie. She is principal investigator on the ACHILLES research program. That's the assessment, costing, and enhancement of long linear assets. And Stephanie's talk tonight is on the reliable infrastructure performance of long linear assets. That's rail and road earthworks, pipeline bedding, and flood protection structures. Old assets are supporting much of our railway infrastructure, so new structures, as in HS2, must be robust to endure the effects of climate change and defy the conditions which are causing concern in our aging railway structures. There's a lot to explain, so may I now hand you over to Professor Stephanie Glendinning to give us the real information on the subject. Thank you very much, Stephanie. It's all yours.
Okay, thank you very much, and thank you for the invitation to speak. So my talk this evening, I'll just give a short background and sort of motivation for the research. I'll talk through some of the research results that we have to date, and then hopefully show some ways in which we're utilising the research results, working with our industrial partners to help kind of inform decision making around about managing these assets. And I'm particularly going to use railways as an example. Okay, so kind of setting the context, I guess we're all kind of aware of this in the main, that particularly our transport infrastructure is some of the heaviest used in the world. It always amazes me to have this pointed out, that our rail network takes 50% more traffic daily than the French network, despite the difference in the size of the countries. And yet, you know, our underground system and much of our railway system is also some of the oldest in the world. And some of that is, you know, over 100, some of it over 150 years old. And it has deteriorated, it's deteriorated substantially, and we observe failures on that network, and sometimes difficult to explain why those failures have occurred at a particular time when they haven't occurred previously. So how do we understand what causes of a failure at a particular time and in a particular location and not at another time? And it's quite important to be able to understand that, because our transport infrastructure is so heavily used, a small failure on that network quickly cascades and becomes quite a significant problem. So across a very wide geographical area. So the sort of illustration there is a failure near Birmingham then has cascaded to Scotland, across to London and down to the tip of Cornwall and into Wales. So failure is a big deal. In terms of its relationship to weather, then we kind of, again, we've all probably experienced almost anecdotal information that when it's wet, we get failures, particularly on the railway. So this was 2012. It was characterised by a wet summer, which is actually important, because part of actually what we found holds up our clay, particularly our embankments, but also to an extent cuttings, are the suctions that build up in those materials. They build up in the summer because of that, usually because of dry weather. And when it's wet in the summer, those suctions are don't last as long, and sometimes that loss of suction causes that triggering of failure. And this is showing the summer of 2012, but we also last summer in a wet period had the unfortunately fatal crash at Carmont in Scotland. And looking at some data related to the effect of rainfall on failures across the network. This is a plot of soil moisture deficit, which is basically the amount of extra capacity that you've got in the soil to take on more water. So when the soil moisture deficit is 0, there's more or less no capacity to take on more water. And this is a plot with time across the x-axis. You've got greater deficit or greater suction that's brought about with large trees, which is the hard line, the dotted line, which is grass. And then the failures that occur around the network on the earthworks in London Underground and what was then rail track are when the soil moisture deficit is 0. So that's when it's wet. So we've got evidence to say that wet weather causes or is a trigger to failure. The work that I'm going to describe, we have concentrated on clay materials. They aren't the only materials, they're not the whole picture, but it's just where we've started. And just to illustrate that's, it's a minority amount of material, but it's still significant because it occurs over quite a wide part of the network and part of the network that are most densely used. So it's just to point that out, that's the scope of what we've done. And what happens to those materials then, it's not just about wet, but it's also about the cycles of wetting and drying from summer to winter. And those cycles then, one of the effects of that is to cause that shrinking and swelling of those clay materials that then, this is an embankment that then causes the differential movement of the track, which causes serviceability state failure. You can see that there illustrated very well in that photograph. You can also see the out of true signals. And we also believe actually that then this shrinking and swelling action, and I'll come to talk about this in a bit, it has the potential to then go on to actually lead to ultimate limit state failure. And this is an example, obviously it's a cutting, but this material here has deteriorated and then caused a failure, which is obviously causing great disruption. And this is the London to Bristol line, which I'll use as a case study a bit later in the talk. So it's saying, weather has the effect of wetting, drying that causes potential long-term deterioration. It also has the effect of potentially causing a triggering effect to failure. And what we wanted to do was kind of understand these processes and these triggering events so that we could be more informed about how to manage this across the network. So the ACHILLES programme then, as I said, is concentrated on clay materials, but our aim is to add to the knowledge base that can deliver a more consistent and affordable and safe services, and to add to the data about intelligent design and management and maintenance. And we are going to concentrate, today I'm going to concentrate on railways, because railways are older. There are quite a lot of failures on the rail network, and that actually the failures are far more costly and disruptive than predictive maintenance, and that actually we could save a lot if we could more intelligently go in and put preventative measures in. So the work, again, it's not starting afresh. We've got a long history of working and to draw out, this is a collaboration across a number of different universities. We're working with Loughborough, Durham, Southampton, Bath, Leeds and the British Geological Survey. And we're working together with our industry partners. So we're working with Network Rail, Highways England, London Underground, and a range of their consultants. And also the Environment Agency on flood embankments, but that's kind of another story. And because we've got a long history of working with the industrial partners, we get to kind of understand more about how they manage the assets. So this is the Network Rail or Earthworks technical strategy. And you'll see in this, it's about, being able to prioritise targeted interventions to reduce risk. It's about looking at resistance to weather, being able to look at some sort of future proofing to forecast what happens in the future so that we can add preventative and predictive maintenance. And this is where we want to feed in our research results so that we provide something that's actually useful and tangible to managing the assets. And so the programme is conceived around this framework of whole life performance. So this diagram is saying that over time, an earthworks asset takes a small amount of time to bed in after construction, has a lifetime over which it is performing adequately, but is constantly deteriorating. And some of the driver of that deterioration is through weather, this wetting and drying processes. And at some point in its future life, it becomes unreliable and reaches some sort of performance threshold, whether that is serviceability state failure or ultimate limit state failure. And what the Achilles programme then is doing is trying to understand the deterioration processes of the soil, the sort of science bit. That's Research Challenge 1. In Research Challenge 2, we're looking at what the implications of that are on the performance of the asset, and thinking about how we might intervene in order to bring the performance back up to reliable. And then Research Challenge 3 is about how we produce forecasting tools and use those to aid decision making for the asset owners. And I'll talk a bit about each of those research challenges. So first of all, then, through our previous work, we came up with a kind of model of clay soil deterioration under the effect of wetting and drying, essentially. So if we start in the top left, in the orange quadrant, we've observed that if you wet and dry a clay soil, it breaks down its microstructure, and we observe micro cracking. And because of that, those micro cracks, it means that at the same water content, a clay soil cannot hold on to the same amount of suction. And so because of that loss of suction, it loses strength. And then eventually that loss of strength will then cause movement, and movement in a slope then causes, with time, downslope ratcheting. And because it's straining, it causes strain softening, which can lead to ultimate limit state failure. The micro cracking can also then lead to changes in the way that the water moves in and out of the slope. and can actually accelerate that deterioration because of more water movement. And it can also cause visible macro cracks, which can then lead to vegetation penetrating further, which further exacerbates that wetting and drying process, which can further accelerate deterioration. And this is our framework that we want to then study at the laboratory scale, the numerical modelling, and at the field scale to tie all of that together. So firstly then, in terms of the laboratory work, and this has largely been done by colleagues at Durham, led by David Toll. You can see then at the top left, these are scans, images of clay soil that has undergone the wetting and drying. And you can visibly see then the breakdown in this structure with the further wetting and drying cycles. You can see those micro cracks actually happening. And then we can see in the graphs the sort of changes in suction with degree of saturation. And we can also see with the plots of void ratio what this means to the voids within the clay soil. So this is a set of laboratory results that illustrate that deterioration of the clay with the action of wetting and drying. In order to be able to utilise that within a numerical model, we've needed to produce a constitutive model that actually models mathematically the damage that is caused to the clay with wetting and drying. And this has been done by my colleague Mohammed Rouhania. And the plot on the right just shows that for different water contents of clays, this model has been able to reproduce with the wetting and drying cycles the loss of strength. And that's been validated against laboratory experimental results. Moving on then to the numerical models, what we've needed to do with our numerical models is to be able to produce something that can start looking at developing a forecasting tool that can actually look at modelling wetting and drying from actual weather on an actual slope and look at how that changes the performance of the slope with time. And we can quantify performance in a range of ways. And on this slide, it's with factor of safety. So the model we've developed can take a weather sequence and simulate. We've validated that the graph at the top there is looking at poor water pressures at different depths in a slope, and we've measured those within a slope that I'll mention later. And we've been able to use it to produce the downslope ratcheting effects that I mentioned earlier. And we validated that against others' work in a centrifuge. And then we've utilised this to then model factor of safety with time over a number of years. And this has given us one first insight into what might be, one of the reasons why slopes will fail with the same weather event where previously they've not failed, because actually what you see is if your factor of safety is reducing with time, if actually you imagined this factor of safety at the bottom to be about 1, then you could imagine that one of these winter events could trigger a failure here, whereas it didn't early in its life because it wasn't near the factor of safety of 1. So it was just giving us just a small thing to add to that conversation. We've then needed to look at future climate, and we've used the UKCP scenarios to do this systematically. we've not been able to use them directly because they give you lots of random weathers, which have extreme events at random points, which causes our models to then fail at random times. So we couldn't do designed numerical experiments. And basically what this model is saying, this slide is saying, is that we had to construct our own weather event series in order to drive deterioration rather than to trigger failure. And this slide then is to start to sort of look at the implication using our numerical model with our designed future weathers. We've started to produce these deterioration curves. These are factor of safety, but the critical one on this slide is bottom right, that's saying that you can see with the future climate, which is the red line, that actually we've driven the material closer to residual strength quicker with a future climate than we have with the current climate. So this is starting to give us insight into the fact that climate change could accelerate deterioration in our clay slopes. The other thing we've done with the model then is to look at, factor of safety with time. And this is a plot that's the early part of this plot is similar to previous work that's looking at, this is just pore water pressure alleviation in the cup slope. But over time, you're actually getting this breakdown of the material surface, and that is what is causing failure. And that's just then showing that the critical failure surface moves from something that is a bit more deep-seated to start with to something that's shallow in a clay cutting, rather like that photograph of that failure on the London to Bristol line. We have also put designed triggering events back in. So we've looked at long-term deterioration, but we've overlain that with some designed extreme events. And again, the effect of that is to both accelerate deterioration, but also then potentially to trigger failure because your factor of safety is lower. And to observe how it does that is in this slide, where you're actually causing the wet period, so that's a wet period there, is causing an increased movement downslope. And it's that sort of acceleration of the ratcheting by the wet event that is accelerating that movement and that reduced factor of safety. What we can also do with the model is to look at slope interventions. And again, the types of interventions and the design of those is being informed by our industry partners. And instead of looking at the change in factor of safety that's been achieved by a slope intervention, we've looked at the extension to life. So in this example, and this is more conceptual at the moment, but it's saying that if this is our deterioration of our slope with time, if we intervene early in its lifetime, when it's not too far deteriorated, we get a 50% increase in serviceable life by our intervention. Whereas actually, if we wait until it's seriously deteriorated or failed, you get much less of an increase in serviceable life. So it's starting to give us that kind of pointing towards that kind of financial benefit, if you like, from doing preemptive interventions or maintenance rather than leaving the slope to fail, because actually you get better extension to life from doing that. The other thing we've done with the models is started to scale up. So instead of just looking at single slopes, we've started to look at the effect of over a whole line. And this is where that London to Bristol line has come in. We've used this as a case study. We've used it, we've also looked at the road at the M4, and we've taken some of our information from one of our field sites that's on the A34, but that's a sort of by the way for the purposes of this presentation. Really, we've looked at that red line, the main line between London and Bristol. And what we've done to sort of narrow down the number of numerical models we've needed to run, because they're quite expensive in terms of time and effort, is to take the LiDAR data from the London to Bristol line and to look at a range of slope angles and heights that are most representative of what occurs across that corridor. And we've also used basically one set of material properties, and we've found this to be sort of reasonable. We've taken London clay soil parameters to use in the model, because actually if you look, most of the material, well, almost all the materials along that line classify as the same sorts of geological materials. It's not perfect, but it was a reasonable thing to do to try and look at the whole line. And then what we did was we plotted slope height and slope angle along that line and looked at factor of safety with time. And we've taken it from time of construction through to present day. And so the green dots are things that have a factor of safety above 1, and the red dots are below 1, and the others are sort of borderline. And as I step through, we can see how that develops with time, and you can also see the dots along the line for the cuttings as they move towards failure. So I've kind of can move that through, and you can see the dots change on the line as well. So you can see with time that more slopes become less stable. And we've compared these results with those from a study from Mott MacDonald, looking at the real data from similar materials around the rail network. And the plot top left is the same geometry and the slopes, and the red dots are real failures. So actually for the network, actually the models are producing results that are in line with the observed results out there on the network, which is kind of very encouraging and quite exciting for us, that these tools are really replicating what's happening out there in the field. And the next step to create tools that are useful in asset management was to take those model runs that I've just described and to work with our mathematics colleagues at the university, led by Darren Wilkinson, to design mathematically a set of numerical experiments that allow us to extrapolate between those experiments to look at a wider set of geometries and materials, but in a statistically valid way. So we did sort of 76 mathematically designed numerical simulations and used a range of soil properties. to then produce a numerical tool to allow us to look more widely across the network. So, you know, we did 76 numerical experiments that took 40 days with 10 machines working to produce this emulator, which is a sort of fancy tool for extrapolating between parameters. And you can then produce 900 models worth of output in 5 hours with one machine. So you can see the power of doing something like this. And we've used this to create an app that allows you then with a slider to change the soil properties and will instantaneously produce you a deterioration curve. So on this side, then you can change the cohesion, friction angle, permeability. You can do that with a slider. Let's, I think if we do the London to Bristol prediction, I hope this works. If I run the prediction, yeah, so instantaneously using that, you get then a similar sort of plot that gives you at the top, for the different geometries, you get this time to failures. And it also produces you a deterioration curve for factor of safety with time. So you can see the power of that to be able to do that instantly. I'll stop the share and go back to my other screen. I think, hopefully, and if I move, is that working? Yeah.
Yes.
So, and it looks like magic. It looks like magic to me anyway. But the results of that emulator still sit very well when compared to the real data. That's just this sort of the real data that's actually been recorded from the actual failures around the network. So the power of this tool is then to be able to look at existing lines and to be able to do quite a quick look at the different geometries and the materials very quickly, or actually it could be used in design to be able to look at, you know, your different soil properties and to look at different geometries and look at those deterioration curves with time. And we're working with Network Rail on the one hand and HS2 on the other hand to look at using this tool in practice. Just a few things then before I kind of try and bring all of this together in one place, is that we've been wanting to actually kind of understand this concept of deterioration and asset life and performance more fully with what it actually means in real life to the different asset owners, and how we might use that to understand what performance thresholds are in order to be able to then start working on interventions, when to do those, how to cost them, and to look at the economics. And this is a piece of work that's in progress. We're developing tools to go out and measure and rapidly assess the current condition of an asset with our colleagues from British Geological Survey. And we're doing that, we're enabled because we have a number of different assets that we're monitoring ourselves and have done over a long period of time. So top left is the test embankment that we constructed back in 2005, and we've got long time series data from that. So we've done that from Newcastle. There's a highways cutting near Newbury that colleagues at Southampton have been looking at. And we've recently taken on a flood embankment. Well, it's just near Hexham. And all of that together is allowing us to experiment with different monitoring and modelling tools in order to be able to work on rapid characterisation. And then sort of finally then to bring all of these bits together is just to sort of say one of the outputs we're trying to look at is this concept of a condition assessment strategy. So it's sort of saying you can look at a route, you can use the emulator to take a very quick look at that route and to look at the materials and the range of geometries to give you a sense of where your vulnerabilities are across that route. And then having got those vulnerabilities, we can then use our more sophisticated numerical tools to take a look at those vulnerable parts more carefully, to look at what failure modes might actually look like and where that asset might sit along the deterioration curve based on its history, etc. We can then look at going in and appraising that asset with some monitoring techniques, and then start looking with the asset owner around, what are the performance thresholds for this particular asset based on its utilisation and its condition. Then we can start looking at what interventions we might be able to put in preemptively to extend the asset life, and to look at then how much that costs. So how much does it cost to put the monitoring in? How much does it cost to intervene? Versus how much would it actually cost if you got a failure on this line in terms of disruption, fines, and the sort of social and economic cost of all that disruption to the users of the network. And that ultimately, in the next part of the research, is where we want to go, and where all these various pieces all come together in the sort of decision support. And so the next phase is we're looking at more monitoring, condition assessment, as I said, performance. We're trying to emulate then the climate scenarios and the remediation options. We're working on design guidance with HS2 and looking at those kind of commercial and societal impacts. And instead of having our 3 research challenges, we're now kind of looking at monitoring, performance, simulation and design, essentially, and pulling all of those things together with working more and more closely with the asset owners. So with that, there is more information on the project website, and there's also a chance we can have a kind of chat now. But if people think of things in the future, then that's my email address.
Lovely. Well, I've got to say that was absolutely splendid, Stephanie. From your initial pictures of the distorted railway lines and tracks, I was quite worried to begin with, but with confidence and looking at your procedures,
hopefully.
Oh well, I'm confident. I think you've really gone all the way in trying to find out how these things happen and how long the infrastructures are going to last. And I'm very, very impressed. But let's have some questions. If anyone would have a question for Stephanie, could you please quote your name and your location or the company you're working with? Thank you.
Lovely. I suppose with the announcement today of GB Rail, I suppose it gets one thinking. Are companies is there a joined up thinking across the railway network that would be willing to adopt this, or is everything too fragmented and people are sort of trying different ideas all over the place?
Good question. I don't know is the answer to that. So I'm not. I try to get. We've had a bit of an email correspondence, a few people today about the possible implications of of today's announcement. I'm not sure I'm not sure really actually what the difference is going to be, to be honest, in what's been announced today. Whether it might possibly create a difference in terms of the penalties and fines that are imposed because of delays, to slightly shift that financial model. I don't know. I don't know enough detail. Interestingly, I've just started to talk to somebody from a different person from Network Rail who's been looking at the impact of extreme events, has been involved in the post-Carmont investigation, and hoping to work with him on trying to do this better join up between weather preparedness and the whole systems view, because currently, you know, there's information about the kind of the weather events that trigger failure, but actually it's not just the weather event, because as I've shown for clay materials in particular, there's an effect of antecedents. So there's not just the event, but then there's the history behind the weather history behind that event. But then there's also the state of the asset and the condition of the asset and its state of deterioration relative to that event. So that's sort of a join up that's not yet happening that I'd like to tackle anyway, but there's so much to do.
No, that's fair enough. It's nice to see the old Durham XRCT going again. That was some excellent images, and yeah, also the join. This is why the cross country is always late when he gets to Newcastle by about 9 o'clock. I think that explains everything.
Can I make a question or a comment? I live in Sunderland at Seaburn, and we often go on the beach to the Whitburn end, which is boulder clay and other glacial deposits. This year, there's been an awful lot of land slipping or cliff slipping, classic rotational slips, which I haven't seen so much in the past. It's very apparent this year, this winter. I'm assuming that is a weather-related effect, that you know, dry in the summer, very heavy rain last winter has caused this rotational slip in the cliffs. Would I be right in that?
I would imagine that these deterioration processes that I've sort of been talking about in the clay soils would also apply in that particular context. So it's both the long-term wetting and drying that these materials will undergo that causes the change in their structure, that then makes them then more susceptible to the weather event that happens in that short time frame. So it's a kind of combination of long-term deterioration coupled with any localized weather event that causes the trigger to the actual failure. So yes is probably the short answer to the question.
Yeah, I mean, one thing I noticed, it's gone now, but about 2 months ago, you could actually see slicken sides on the curved surfaces of the clay. It is a classic you know, slicken side situation where it had failed and slid down. Yeah, it's a very interesting, but there's been so much slip and coastal erosion this last winter. Obviously, it's a cumulative effect, but suddenly these failures have taken place. Anyway, thank you very much. Yeah.
Thank you.
David, did you have a comment?
Wondering, sorry, I was David Bell, Newcastle. I was wondering what extensions you were considering for the future for the research. I think about kind of vibration, that's I've seen kind of that kind of affect the solidity of materials. and kind of the amount of traffic on the connection, traveling down to London on a fairly regular basis on a Sunday, every now and again you'd be going on an old line that was normally out of service for passengers, and they were using it because they were doing some work on the main line, and you can always have the impression that they were going at a very, very slow pace indeed over certain areas. And I'm just wondering, kind of the speed of the travel, would the increased vibration cause problems?
Yeah, the vibration effect is not something I know about myself. Speed restriction, I mean, yes, so vibration obviously in certain materials can lead to that build up of pore water pressure effect. Speed restriction is also imposed if you've got lack of alignment of the track. So it could have been for that reason as well. So that's that bit. But in terms of the future of the research, there's so many directions that we could go in. One of the things we're doing is extending to look at flood embankments. So there is the additional failure mechanism of the actual flood. So there's the wetting and drying that is occurring just like the transport embankments, but then of course also couple that with a flooding event, a saturating event, and then the drawdown. So we want to look at that, but you could also apply that to a transport situation when you get a flood next to a transport embankment. So by accident, so I know that happens, and I've been on the train just near Durham when there's been that flood next to the embankment, which was quite scary, I have to say, one time. But also intentionally, where there is discussion around using the embankments for the east-west arc line between sort of Milton Keynes, Oxford and Cambridge, around intentionally using your embankments to also be flood protection embankments. So there's quite a bit of work to do there with that additional kind of failure mechanism, just as one thing to look at. But you know, there's other materials. We've looked at clays. There are other materials to look at in terms of their the influence of wetting and drying and climate change on those. Lots to do.
Do we have any more questions? I think they're being shy, Stephanie. I think they're holding back to talk to you later, perhaps, once they've formulated exactly what they want to ask.
It's fine. We can send questions through, and then I can sneakily ask other members of the team to also help with answering them.
Oh, thank you very much indeed, Stephanie. That is, that's a very, very good offer, and I'm sure all our members will think of something soon and come up with them and ask you these questions. But until then, thank you very, very much indeed. It was very, very enjoyable. And,
thank you. It's a pleasure.
Can I pass you across now to Robert Fowle, who's going to give the vote of thanks for NEIMME members.
Can you hear me? Thank you, Stephanie. I think it's a while ago since we last met at
it is a while ago, yeah.
Board in Glasgow. You obviously got home safely that evening.
Yeah.
Well, I must admit, a very impressive presentation. I'm a little worried, bearing in mind that railways have been around coming up to 180 years. Infrastructure is certainly in need of inspection. In my area, tunnels, yours are slopes that you're working on. I was quite surprised there were 143 rail earthwork failures. I can now understand why there is disruption to the rail network. So your work is highly relevant, and hopefully the future climate change will be halted so that we have factors of safety that will serve us a few more years into the future. It's certainly an interesting topic in that sense, and your interactive modeling was very impressive, and certainly a practical slope life tool that I would find other applications for, not just rail embankments.
Mhm.
And a personal note, it seems to me that RS2 definitely needs some help reading my ground engineering. They're not exactly excelling at the moment. Anyway, I would ask all those that are able to show their appreciation in the normal way by producing clapping sounds or waving in this case. And hope you get plenty of interesting questions from your presentation.
Thank you. Thanks very much. Much appreciated.
Thank you very much indeed, Robert. That's very, very kind of you. Let's move on with what's going to happen next. Andrew, would you like to tell us about the forthcoming meetings and such like?
So yes, no, thank you again, Stephanie. This is quite. It may well be what Stevenson, the civil engineer, may well have been doing today if he was still with us. In terms of future events, we have our next lecture in June. As with the Royce Institute, predominantly looking at how we can combat corrosion in a range of industrial settings. So that should be very interesting indeed. And of course, don't forget about passing the word on about the Tunnicliffe Medal. Again, just go to our website, all the details are there, but it's open to all engineers across a broad range of engineering disciplines under the age of 35. And we'd be, ourselves and of course the Midland Institute of Mining Engineers would be very grateful to all who apply to it, because so we can have a very interesting competition indeed. I think that's all the notices, Steve. Do come along to our June lecture, as we'll be doing a short review of the year as well, if I can sneak that in. But that's all from me this time.
Well, thank you very much, Andrew. Well, that made an absolutely spectacular evening. Thank you very much, Stephanie, and I'd like to thank all members and guests for attending tonight. And I'm sure you are as impressed as I am with what we've been given. And so thank you everyone for coming along, especially to you, Stephanie, for a wonderful presentation. And I'm sure, you know, anyone who's missed that will be very, very keen after everyone's told them to have a look at the recording of it. So thank you very much, and thank you everyone for attending tonight. And we'll see you at the next meeting. Thank you.